Students, welcome to Global Virtual School. This is your chemistry first class. I am Dr. Ijaz Mano, and we are on chapter 2, that is atomic structure, and the topic for today's discussion is hydrogen spectrum. Students, after completing this topic, hydrogen spectrum, you will be able to explain the Zeeman effect and Stark effect. If you remember in our previous lecture that was on defects of Bohr's atomic model, we defined the Zeeman effect, that's splitting of the spectral lines of hydrogen spectrum. When magnetic field is applied, then this is called magnetic effect, and a splitting of the hydrogen spectral lines by applying or under the influence of electric field, then this is called the Stark effect. This will be explained by this hydrogen spectrum. I will just quickly recall the defects of Bohr's model, that Bohr's model is applicable to one electron system and it do not explain the spectrum of multiple electron system. Its second defect was Bohr's theory cannot explain the fine structure of hydrogen spectrum. If a high resolving power spectrometer is applied to hydrogen spectrum, the spectral lines are further divided into fine lines. This was not explained by Bohr's atomic model. Similarly, Bohr suggested the circular orbit of electron, but it was actually electron revolve in 3 dimensions. And Bohr's theory also could not explain the Zeeman and Stark effect. First, I will let you know what is spectrum. Spectrum, students, basically this is the visual display. You can say we can see with our eyes a dispersion of the component of light. When it is passed through a prism or spectrometer, then this is called spectrum. Let I show you an example. This is symbol of white sunlight. When this is passed through a glass prism, this is divided into further spectral lines, and this visual display of different colors, this is called the spectrum, like violet, indigo, blue, green, yellow, orange, red. Then this is called the spectrum. Another example is nature spectrum, like is the rainbow. Here in this case, water drops, they act as prism, and when light pass through this prism, they further split into a different spectral line, they show different colors, and this visual display, this is called the spectrum. Then we have spectrums are of two types. Continuous spectrum, I just told you about the rainbow, that is a continuous spectrum. And continuous spectrum, actually this is the characteristics of material in bulk, or you can say a white light, that is the sunlight, that usually provides the continuous spectrum. And in continuous spectrum, there is no demarcation of the colors. One color is diffused into other colors. You cannot say red color is stopping here or yellow color is stopping here, just they diffuse into each other. There are no proper demarcation lines for different colors. Another type is line spectrum, and line spectrums are those spectrum in which there are proper demarcations, proper lines are properly separated, and they have further two types, line emission and line absorption. And the atoms are usually they are characteristics of the line spectrum, like hydrogen spectrum, sodium spectrum, and I will explain you in this topic how they are giving you line emission and line absorption. Okay, let's say what is continuous spectrum, in which different colors are diffused into each other. There are no proper demarcation where this color is, blue color is ending and where the green color is starting. So this is the continuous spectrum. In line spectrum, they have demarcation lines. One color is separated from the other properly. But in line emission, you say when electron jump from higher orbit to lower orbit, they emit the radiation of a particular wavelength and particular wave number, and they give a particular color that appears in the form of spectrum. From any higher orbit to the lower orbit, they show their lines, and the background is the dark when they are emitting the lights, only just emitting light. While in case when electrons move from lower orbit to higher orbit, they absorb. Wherever they absorb, there is the dark line, because now they are absorbing, and now background is the bright. So this is the basic difference between absorption line and emission line spectrum. In exam you can be asked what is the continuous spectrum, what is difference between continuous and line spectrum. Even can be asked what is difference between line emission spectrum and line absorption spectrum. And now I'm talking about the hydrogen spectrum. Hydrogen, let you have hydrogen gas in a cylinder enclosed in a container. They have atoms of hydrogen, and you know it's the an electron. They have orbits, electron, and just to make you more clear, I am drawing this. When we heat it, when it is heated, electrons take the energy. This electron, like this, they take the energy, absorb the energy, and move toward the higher orbit. So because they are absorbing, at that point there will be a dark color, because at that point they are absorbing energy. Now stop heating and you have gas, like heated gas, like it's the hot gas. Now what will happen? Because electrons are stable in the lower energy states, the excited electrons, they will start moving back to the lower energy state. In this case they will emit the extra energy, and this will appear in the form of a color, in the form of a bright lines, and the while all the background will be dark. So by the excitation moving from lower to higher, and by de-excitation moving from higher to lower orbit, they produce the spectrum line. In this case, when you stop heating and when this light is passed through a spectrometer, they produce light emission spectrum. And we can calculate the wave number, value of the wave number of these radiation using this equation. R is the Rydberg constant, that is the combination of different constants, and it has a constant value, and you can use this equation for calculating the different wave numbers. And we have these in the form of series, like a Lyman series, Bohrs series, Parson, Reckitt, and Fund series. In Lyman series, when electron jump from any higher orbit to the first orbit, lower orbit is 1 and higher orbit will be more than 1, that is second, third, fourth, fifth, or it can be from infinity. Then this is called the radiation that are emitting, these will be called Lyman series. In Bohrs series, when electron jump from any higher orbit to the second, then in this case higher orbit will be 3, 4, 5, 6 and up to infinity. And then this is called Bohrs series. And in Parson series, when electron jump from any higher orbit to the third orbit, and higher orbit will be 4, 5, 6 and up to from infinity. Then this series, group of series is called Parson series. And then Reckitt series, when electron jump from any higher orbit to the fourth orbit. Fourth one is the lower in this case, and higher will be 5, 6, 8, 7, 8 and up to infinity. And then a Fund series will be when electron jump from any higher orbit to the fifth orbit, and higher orbit will be what will be the higher orbit from the fifth, that will be 6, 7, 8, 9. This will be more clear with this picture. Lyman series, you can consider this is the nucleus of the atom. This is the nucleus. Nucleus contains proton and neutron, and outer them are orbits. This one is the first orbit, like this one, second orbit, third, fourth, fifth. If electron jump from second orbit to first, this will come in Lyman series. If it jump from any higher orbit to first, like third, then this is again in Lyman series. And the radiation emitted will have its own frequency, own wavelength, own wave number. When it will jump from third to first, then it has own type, own value of the this emitting radiation. If it jump from fourth to the first, or 5 or 6 or 7 or even up to from infinity, then you can see This group of series is called Lyman series. If electron jump from any higher orbit to the second orbit, any orbit to the second, third to second, fourth to second, or fifth to second, or sixth, 7, infinity to second orbit, then this is called Bohrs series. And every line, every jump of the electron 3 to 2, it has own its type of radiation. Its value will be different from when it is jumping from 4 to emitted radiation has its own wavelength, own frequency and wavelength. If it is moving from 5th to 2nd, then it has own its radiation. So this group, this is called Bohrs series. Similarly, when electron jump from any higher orbit to the third orbit, let's suppose 4, from 5th orbit to the third orbit, 6th orbit to third orbit, 7 to third orbit, or from infinity to third orbit, then this is called Bohrs series. And every jump, it has its own type of radiation, and it has own value of wavelength, frequency and wave number. Similarly, when electron jump from any higher orbit to the fourth one, like from 5th, 6th, 7, from infinity to the fourth one, then this is called bracket series, And when it jump from any higher orbit to the fifth orbit, like from 6, 7, from infinity to the fifth orbit, then this is called Fund series. So this series, I will explain how we can calculate the wave number of each line. And Lyman series, the radiation of this series lies in the UV, or you can say ultraviolet region, and Bohrs series usually in visible region. Paston and bracket and Fund series usually these lies in the infrared region. Origin of hydrogen spectrum on the base of Bohrs model is that first spectral line were discovered very earlier in 1887 by Lyman and Bohrs. On the base of, they have the name Lyman series and Bohrs series, but no satisfactory reason for these series becomes available till 1913, and in the same year, in 1913, Niels Bohr presented his explanation of why this line spectra is obtained. So it will be even more clear with this video, okay, what is Lyman, Bohrs, Paston, bracket and Fund series.
When an atom makes a transition from the higher energy state to a lower energy state, the energy is radiated in the form of a photon having certain frequency. The spectral lines arising from the transition of electrons of an atom from higher energy states to a definite energy state form a spectral series. The various spectral series of hydrogen atom can be represented with the help of orbital diagram of an atom, as shown in the animation. When a transition from higher orbits to the first orbit occurs in the atom, Lyman series is obtained. The values of frequencies obtained in this transition lie in the ultraviolet region of the electromagnetic spectrum. When a transition from higher orbits to the second orbit occurs in the atom, Bohrs series is obtained. The values of frequencies obtained in this transition lie in the ultraviolet region of the electromagnetic spectrum. When a transition from higher orbits to the third orbit occurs in the atom, Paston series is obtained. The values of frequencies obtained in this transition lie in the infrared region of the electromagnetic spectrum. When a transition from higher orbits to the fourth orbit occurs in the atom, bracket series is obtained. When a transition from higher orbits to the fifth orbit occurs in the atom, Fund series is obtained. The energy of emitted radiation is given by the formula shown here, and the Rydberg formula for the spectrum of hydrogen atom is given by the formula as given here.
Students, hopefully now you have a clear picture about the spectral series, and now I will let you know how you can calculate the values of the wave number for these spectral lines. First we have the Lyman series, and I already told you that Lyman series, one electron jump from any high orbit to the first orbit, then they give the Lyman series, and you can calculate with the help of this equation. And in this case n1 will be 1 and n2 will be more than this orbit, like 2, 3, 4, 5 and up to infinity. And the first line will be when electron jump from second to first, second line will be when electron jump from third to first, like this one. Apply this equation, put the values and calculate, and you can find the wave number of the first line. Then similarly for the second line, using this equation, and n1 in this case is 1 square and n2 in this case is 3, so taking 3 squares and solving this, you can find the second line wave number value of the second line. Similarly for third line, when electron jump from fourth orbit to the first orbit, so putting these values and solving this equation, you must solve this with me so you have even more clear picture about this, and you find the value of wave number of the third line. Similarly you can calculate the wave number for the fourth, fifth, sixth and seventh line and so on. And for the infinity, it will be called limiting line, when n1 will be 1 and n2 will be infinity. So calculating this 1 over infinity is always 0. So this one you can find the value of the wave number. This is for Lyman series. Students, here is the solution of that spectral lines. Apparently Lyman series, when all electrons jump from any orbits to the first, they appear in a single line. But when in deep down you can see when electron jump from third to 1, second to 1, then it has own value of wave number. When third to first, it has own. So each has a combination of different spectral lines, and each spectral line has its own wave number value that represent that 5 lines. Similarly for Bohrs series, this is also a combination of further lines, first, second, third and up to limiting line. In this case, lower orbit is 2 and higher orbits will be 3, 4, 5 and up to infinity. So putting the values in this equation and solving this, you can find the wave number for first line, for second line, similarly for third line, we will calculate for fourth line, and for infinity line, that is called the limiting line. So you can calculate in this way in the wave number for each lines. So these lines are basically this group exists in a Bohrs series. Similarly the Parsons series, the lower orbit is in this case third orbit, and the higher orbits will be 4, 5, 6 and up to infinity. Just apply this equation for wave number calculation and add the values and then solve. For lower 3 and for n2 at 4, taking 4 square and taking LCM and multiplying this, you can find the value of the wave number for the first line. Similarly for the second line, and 1 is 3 and 2 is 5, and solving you can find the value of the second line of the Parsons series. Similarly for third line, for fourth and for limiting line, n1 is 3 and n2 is infinity, and in this way you can calculate the value of limiting line of the Parsons series. Similarly for Racket series, in this case lower orbit is n4, fourth orbit and higher orbits are 5, 6, 7, 8 and up to infinity. So again using the same equation for wave number calculation, add the values, solve it, and you can find the wave number of first line, second line, infinity lines in this case, and just do calculation carefully, and these can be asked in your exam for any type of the line, can be asked from any series. Similarly, one series when electron jump from any higher orbit to fifth one, first line add n1 5, n2 6, taking square of 6, square of 5, and solving this equation, you can calculate the value of wave number for first line, for second line, similarly for third line, and up to limiting line. So this was all about the how you can calculate the spectral lines from each series. Again, just for your revision, Lyman series when jump from any higher orbit to the first orbit. Bohrs series from any higher orbit to the second orbit. Person series from any higher orbit to the third orbit. From any higher orbit to the fourth, then it is called the Racket series. When any from higher orbit to the fifth orbit, then this is the Fund series. And basically these are a combination of different series. That's why further splitting these line shows of different spectral lines due to these spectral series. This was all about a hydrogen spectrum. Hopefully you have understand the why it is the Zeeman effect and Stark effect, why the hydrogen spectrum, spectral lines of hydrogen spectrum are further splitted into fine lines. Our next topic will be Planck's quantum theory, and hopefully you have understand the Bohrs atomic model, its defects, and a few of its the defects were that were explained in this lecture.